Today we're going to spend some time talking about two formats of numerical response questions that we know 100% for sure we're going to see on our diploma exam on June 29th. The first is a graphing question. They tell us that we're going to see a graphing question on the exam. This is not me with any kind of inside knowledge. Every single Physics 30 teacher in the province knows what I know about this. We all know that you will see a graphing question that you're going to have to analyze in order to figure out something. Now, there is a good chance that it'll be a question that you have never seen before. I would suggest that it's probably maybe a 60-40 chance that it'd be a graph that you have never seen before. That's okay. We can deal with it. We've done enough of those graphs that we've never seen before that we can deal with another one that we haven't seen before. The one downside to what we're doing now in preparation for our exam, as compared to the way that we've done these questions up until now, or for the most part up until now, is that all of those graphing questions, or most of those graphing questions that we've done up until now, have been done in labs where you've used Google Sheets to spit out for you the slope of the graph and the y-intercept of the graph. We can't do that on our exam. We have to have another way of getting the slope and the y-intercept. So we've done this before, but not very much. I'm going to go through this with you one more time to refresh your memory on how to use your TI-83 or TI-84 or TI-85 calculator to get the slope of a graph and the y-intercept. And then we'll do a little review of something that we've done many, many times before, and that is how to figure out what to do with that value of slope and that value of y-intercept. So what I'd like you to do right now, everybody right now, is to take out your calculator and your data sheet, your calculator and your data sheet. On the front of that booklet that I posted on Google Classroom this morning on numerical response questions, the very first page is going to be this little summary here as to how to use your calculator to spit out the slope and the y-intercept. I'm going to give you some fake data here, or we'll call it some trumped up data, some fake data, in order to use our calculators as practice to get the slope and the y-intercept here. Here's our data. We're going to say our x-axis is 1, 2, 3, 4, 5, 6, and our y-axis, whatever the variables, are 20, 25, 30, 35, 40, and 45. Now, when you see this question next Thursday, a week and a half from now on your exam, it will not be in the form of a data table. It will be in one of the three following forms. It'll either look like this, with your data plotted like this, or it'll be like this, with your data plotted and a line of best fit drawn for you, or it'll be like this, with just the straight line without the data actually being drawn on the graph. In any one of these three cases, it doesn't really matter. Okay? One is easier than the other, okay? But they're all, we can deal with all of them using the same basic technique. If you see this, then you need to take every x and every y, every x and every y, and enter it into your calculator just like this, with all of your data points. If you see this with your data points but a line of best fit drawn for you, don't draw your own. Okay? Don't trust yourself to draw your own. Okay, if there's no line of best fit drawn, don't bother drawing one. Just enter all the data points like this into your calculator. If the line of best fit is drawn for you, you've got two options. You can enter all the data points just like you did for the first one, or you could take the first point and the last point on the line and just enter those as data points. So in other words, you can draw two data points or plot two data points in your table. If you see this one, then for sure, that's all you're going to do is plot the two data points. Make sense? So if you see this or this, that's good news because the line of best fit is there, and all you're going to do is enter 2 points in your table. But if you see the first one, then you're going to have to enter all of the points in your graph. The good news is, lately, The way they seem to be going on the diploma exam is that they give you either this one or this one. So you have to enter, usually, lately at least, only 2 points. Make sense? But listen, don't panic if you see this. Okay, don't panic if you see this. It just takes you a little bit longer because you have to identify all of the X's and all of the Y's. For this one, you cannot just take 2 points. You have to take them all. All right, let's go through that process now of putting this into our calculator. I want everybody to work along with me on this as we follow these steps here. Let's open up the calculator. Please do the following. Everybody, please do the following. Clear your calculator. Okay, there's a reason that I'm doing this. Okay, you'll see what it is in a couple minutes. Clear your calculator. Second function, mem. Get onto option 7. And then scroll over to all. Now, I'm not going to press that because it's going to mess up on my computer. The software doesn't like to deal with a calculator reset. But on your calculators, you can do that. Click all. Okay, clear all memory, and in a couple of seconds, it should say mem cleared. Not RAM cleared, but it should say mem cleared. Okay, I want you to do that right now for a couple of reasons. One, because I want to ask you what comes next. What are we going to do next? Sorry, somebody said it? Put it back to degree mode, because you know that it's going to be reset on June 29th, and you know it's going to go into radian mode, and you know you want it in degree mode. So every time you clear your calculator like this, make sure it goes back into degree mode. Got it? I'm not sure who's supervising your exam on that day. I'll ask them to remind you to put it back into degree mode, but if they forget to remind you to put it back into degree mode, okay, you in the end have got to be responsible for yourself. Okay, get it back in degree mode. All right, next thing you're going to do is plot this data. Let's assume that we have the first one, because that's the hardest one, right, where we have 6 data points. We got to plot all of these. Again, if you have one of the last 2, diagram 2 or diagram 3, then just pick the first point on the line and the last point on the line and plot those. That's it. Okay, we're going to plot all 6 of these. And here's how we're going to do it. We're going to hit on our calculator, stat. Okay, step number 1, stat. Edit. Now, I've got some data in there already. I'm just deleting it. You shouldn't have any data in there. That's the other reason why I had you reset your calculators, is because it takes all that data that's in there out. So it should look like, when you open up the stat edit, it should look like what it's going to look like on next Thursday to you when you do this. Not if you do this, when you do this next Thursday. Let's enter our data. Our data points were 1, 2, 3, 4, 5, 6. That's my x-axis, and my y-axis was 20, 25, 30, 35, 40, and 45. Everybody enter that data, please. So I've done step 4, I filled in my X column. I've done step 5, I filled in my Y column. Now let's go to step 6, which says stat again. Click stat. This time though, it's not going to be stat edit, it's going to be stat calc. Specifically option 4, linear regression. Press enter. Depending upon your version of the TI calculator, you may have to press enter twice. You may have to press enter 3 or 4 times. Just keep pressing enter until you get your result. Okay, for my version, I'm just going to press it twice, and I get y is equal to ax plus b, where a is 5, b is 15. What's my slope? What's the slope of this graph? Hannah? 5, and what's the y-intercept? Josh? 15. Good. Question? Okay, listen, once we have the values of the x, the y-intercept, story, and the slope, which we can get every single time, no matter what this graph looks like, we can get the value of the y-intercept and the slope with our calculator every single time. Then what are we going to do with it? Well, we got to figure out what to use the slope for and the y-intercept for. There are a number of examples, non-numerical examples, on the handout that I posted on Google Classroom this morning. We're going to go through a few of those examples here right now, in order to give us a little bit more practice on how to use this technique that I taught you in order to figure out what the y-intercept and the slope represent, and then to figure out what you're actually looking for in the question. Let's do the second example here. This says in the context of magnetic force on a current carrying conductor or current carrying wire. Keep in mind on your diploma exam, you're going to have numbers here, right? You're going to have to calculate something. But listen, once you analyze the slope and the y-intercept of this, doesn't matter what you're asked for. That's easy. That's the easy part. Okay, figuring out what the slope and the y-intercept mean, that's the hard part here. So let's do this one. What's the first step? Okay, assuming we've already got the value of the slope and the value of the y-intercept, what's the first step in analyzing this graph? What's the shape of this graph? Shibo? Yeah, exactly. It's a straight line graph. So we're going to use y is equal to mx plus b. We will always do that. You may very well get a nuclear decay curve, which is not a straight line. That will not be the question that we're talking about when we say you're going to get a graphing question. You will get a graphing question that is a straight line graph, and you will have to do the slope and y-intercept. Okay, that's independent of that nuclear decay curve, which you may also get, but there's not much to do with that, right, except up and over or over and down. You will get one of these where, just as Shivo just told us, you have to set y equals mx plus b. No question. Then you're going to relate, as Shivo said, this specific graph to this general equation. The y-axis is what, Shivo? What would it be? Force. Magnetic force in this case, right? Magnetic force on a current carrying wire. What does M stand for? Sorry? No. No. What is M? What is M always in y equals mx plus b? Think back to grade 9 math. What is it? Slope. So we're going to replace it with the word slope just because we don't want to get it mixed up with mass later on. X stands for, where's on my x-axis here? Yeah. Yeah, it's going to be current. And it looks like this is going to go through the origin here, so it looks like there's going to be no y-intercept here, right? So my equation is going to be, for this specific graph, F is equal to the slope times the current, which comes directly from the equation that is y equals mx plus b. Yep. Now, what's next? What's next? Yeah, Emma? Good. Find an equation that matches the variables that you have. Probably 3/4 of the time, that equation is going to come directly from your data sheet, although maybe about 25% of the time, it's going to be an equation that you have to figure out to derive. And we'll do a couple examples of ones that we have to derive here in just a couple minutes. This one is going to come directly from my equation sheet, just like 3/4 of them do. Which equation on my data sheet has magnetic force and current in it? This should be the easy part. Which equation has magnetic force and current, can we? Good. F is equal to ILB. Good. Now, let's cross off things that appear in both of those equations. F appears in both, I appears in both. We're left with the slope is equal to what? There is no y-intercept, so we're just looking for what the slope represents here. Slope equals whatever's left on this side, L times B. Now, this question probably would have given you this graph and said, here's the value of the length of the wire. What's the magnetic field? You would have went through this process, found the value of the slope, given the value of the length of the wire, solve for the magnetic field strength. Or, been given the value of the magnetic field, find the slope, and then from that, find the value of the length of the wire. Make sense? Okay, that is a perfectly legitimate question to be given as one of those use the one of those graphing questions that we know we're going to see. If we get this one, hey, that's great because we've seen it before. We get lucky. Hey, you got a pretty good chance that you see one that you've never seen before. For instance, maybe you see this one, V-stop versus frequency. We've never seen that graph before. We see something that looks a lot like that. We've seen EK versus frequency, and the graph looks almost identical. But in the context of the photoelectric effect, V-stop versus frequency is not the same thing as EK versus frequency. So what do we do? What do we do if we come across a graph that we've never seen before? The same thing we always do. Joshua, how do we start? Right. Y equals mx plus b. And then we plug that in. The y-axis would be v stop. This is not speed. This is big V, stopping potential. M is the slope, always. X is the frequency. And this time, it looks like we do, in fact, have a y-intercept. I don't know what its value is. Doesn't really matter. We'll just say plus b. Can't get rid of it if the y-intercept is not 0 or really, really close to 0. So v stop is equal to the slope times frequency plus v. Now we got to either come up with an equation that's on our data sheet or derive an equation that has v stop and frequency in it, in the context of the photoelectric effect, not some random equation, but in the context of the photoelectric effect. I'm going to give you 5 seconds to come up with that equation. Time's up. Anybody got it for me? Yeah, Joshua? Yep, the special equation. HF is equal to EK max plus the work function. That's our special equation because it's not on our data sheet, right? That's also our 5-second rule equation. Okay, not the 5-second rule where you drop food on the floor and pick it up within 5 seconds, you can eat it. Not that 5-second rule. The 5-second rule that says if you can't think of an equation to use in the photoelectric effect within about 5 seconds, use this one. If when I gave you that 5 seconds, you didn't know what the answer was, you should automatically go to this one. Now, it has frequency in it, but it doesn't have v stop. But the nice thing about this equation is that I can do some substitutions to make it look way different. Now I've got v stop and frequency in it. Now I've got to rearrange this to solve for v stop so it looks the same as this. It takes the same form. I'm going to say qv stop is equal to HF minus W, and I'm going to divide by Q. I get V stop is equal to HF over Q minus W over Q. So I divided both terms by Q. Yeah, you can do that. I don't actually do that, but you could, yeah. Now I'm just going to cross off things that appear in both. V stop appears in both. F appears in both. Okay, what am I left with? The slope is equal to, anybody? H over Q. So this question could have given you the value of the charge. You would find the value of the slope using your calculator. You might have to find Planck's constant that way. Or maybe it gives you Planck's constant and it says, what's the value of the charge? Probably not, because it would be an electron, right? You already know the value of the charge. What does the y-intercept represent? 1 sec. What does the y-intercept represent? Yep. Good. Negative W over Q. So maybe in this question, you're given the charge and you need to find the work function. The y-intercept you would get from your calculator, right? Because the calculator spits it out for you when you do that process that we went through a minute ago. Got it? Listen, if you can get the slope of the y-intercept from your calculator and you can do what we just did, you are set. You are set. Let's do one more that is also unique that you haven't seen before. It's the one at the bottom of this page, which again also appears in the booklet that is on Google Classroom for you guys. In the context of a suspended oil drop in the Millikan oil drop experiment, electric field versus weight of the drop. First step. First step, yep. Good. Y equals mx plus b. Man, I'll tell you, if you don't write that down when you see this question on your exam, okay, you don't deserve to get that question right. This is what we do every single time we have a straight line graph. And then let's replace y with, oh, and what's y get replaced with here? E, right, which is what? Electric field. If it doesn't have the arrow over it, it's energy. If it has the arrow over it, it's the electric field. So we're going to say y is E. What's M get replaced with? Kristen, what's M get replaced with there? Yep, good. The slope. So we're going to say electric field is equal to the slope times. Well, this is a little bit trickier. What's X get replaced by? The weight, but what variable do we assign to weight? What is it? mg, or we could say the force of gravity, or you could say m times g. Either one of those would work. And it looks like the y-intercept here is 0, so we can get rid of that, unlike the last question. All right, let's say we need to get an equation either from our data sheet or derive one that relates to electric field and force of gravity in the context of the oil drop experiment. Anybody know which one it is? For a suspended oil drop in the oil drop experiment, we would say, Hannah? Good, Fe equals Fg. So it's not on our data sheet. We had to derive it here, but it's not a very hard one to derive. Fe is Q times E. Fe is, well, as Liam said a few minutes ago, Fg was M times G. But since I filled in Fg here, I'm just going to leave Fg right here, right? If Liam had to put in Mg in the first equation, then he'd put in Mg in the second equation. Let's rearrange this to solve for electric field. So it's solving for the same variable. I get Fg over Q. So what do we got here? Start crossing things off. E disappears because it's in both. Fg disappears because it's in both. What are we left with? The slope is equal to, slope is 1 over Q, not Q, because Q is on the bottom here, right? Slope is equal to 1 over Q. So this question probably would have asked you for the charge of, not of an electron, but the charge of an oil drop. Yep. Yep. Is that all right? Listen, guys, go through all of these. Make sure that you understand all of these. There's no numbers with them, but that's okay. If you understand the concept, then it's just a matter of using your calculator to get the value of the slope and the y-intercept and solving for whatever. In the practice questions that I posted on Google Classroom, there's also a few examples of these, some real examples that have appeared on previous exams. You ready for this? You're going to see it. Now, what else are you going to see? We also know that we're going to get another type of numerical response question. This one is a little bit newer to you. This one is the one that we call the physics principle numerical response question. You will get at least one set of two questions that kind of go together. You'll get at least one set of those. They will probably be the last two questions on the exam, question 49 and 50, although not necessarily. Though the first of the two questions, the first of the pair, will be a question like any other numerical response question that gives you some data, some information, and you have to solve for something. Just do it like you would any other question. But the follow-up question is a little bit different. The follow-up question asks you how you did it. What are the physics principles that you used to do it? This is what takes the place of the written response questions that we had years ago. It used to be that we had 30% of our exam was made up by written response, where you could get marks for doing work even if you got a wrong answer. They replaced that with a machine-scored numerical response question that asks you to identify a couple of physics principles that you use to solve another numerical response question. These physics principles, 0 through 9, are listed on your data sheet in the bottom left-hand corner. Everybody should go to their data sheet right now, find those physics principles, and make a couple notes on those physics principles that I'm going to make as we go through this over the next few minutes. We should be familiar with these already, more or less, but we're going to go through these, all 10 of these, just again, one more time, just to make sure that you're okay with it. Physics principle 0, uniform motion, refers to objects that are moving at a constant velocity. Or technically it could mean at rest, like suspended. It will almost certainly be, though, something that's moving at a constant velocity. One of the equations that you may have used in association with that is V equals D over T. If you've used V equals D over T, you have used principle 0. You know that 100% for sure. Accelerated motion where the net force is not 0. This is when something is accelerating. And typically there, you'll have used A is equal to delta V over delta T, or you've used one of the other acceleration equations. Vf squared is equal to vi squared plus 2ed. D is equal to vit plus 1 half at squared. Something that involves acceleration. These two are usually pretty obvious. If you've used principle 0 or principle 1, you're probably going to know it right away. Uniform circular motion when the object is moving in a circle. Here, the equations that would probably go along with that would be A is equal to v squared over r, the centripetal acceleration, or F is equal to mv squared over r, the centripetal force. Now, a couple of words of caution about this one. Number one, if you're using uniform circular motion, that's technically accelerated motion as well, right? You can't list both. Okay, you can't list both. If it's moving in a circle, list principle 2, not principle 1, even though technically it is accelerated motion as well. They won't give you credit for listing both of them. It's moving in a circle, list principle 2. Now, the second thing that I want to point out to you is that the centripetal force equation doesn't actually appear on your data sheet. You see A is equal to v squared over r, and you see A is equal to F over m. If you put those together, then we get F is equal to mv squared over r. So know that we're probably going to use that question on our exam, or sorry, that equation on our exam, but that it's not on your data sheet. You can either remember it or you can figure it out like we just did. Work energy theorem. In all honesty, you're probably not going to end up doing this one because this is more of a physics 20 thing, but just in case, work energy theorem says that work is equal to the change in energy. Sometimes you'll have set that equal to F times D, force times displacement. Conservation of momentum, I'm pretty sure is pretty straightforward for us. Conservation of momentum, it's just Pi equals Pf, a collision or an explosion, right? Conservation of energy. Conservation of energy is EI equals EF. QV, probably going to be QV equals 1 half mv squared. Maybe QV plus 1 half mv squared equals 1 half mv squared. Maybe conservation of energy is HF is equal to EK max plus W in that photoelectric effect equation. You guys know what the conservation of energy is, though. Conservation of mass energy. What equation would I use in association with that one? Conservation of mass energy. This is easy. Conservation of mass energy, yeah? No, not quite, no. Yeah. Yeah, E equals mc squared. There's your tip off right there. Mass dash energy, conservation of mass energy equals mc squared. Conservation of charge in nucleons. Conservation of charge we use in a number of places. Rub two things together. Okay, the charge transfers, but it's not created or destroyed. Touch two things together, the charge balances. Okay, where else do we see conservation of charge? In a nuclear reaction. Let's say we have carbon 14 and it goes beta decay, produces nitrogen 14 and an antineutrino. If we're trying to balance the atomic numbers, that's conservation of charge. If we're trying to balance the mass numbers, that's conservation of nucleons. Number of protons and neutrons, nucleons, that's what we're doing if we're balancing that mass number. In wave-particle duality, we learned briefly about the wave nature of electrons, although we didn't learn any equations associated with that. Remember the de Broglie hypothesis? Electrons behave as waves, go through both openings, diffract, interfere with themselves, produce an interference pattern, the wave nature of electrons. We didn't do any math with that. The mathematical wave-particle duality would probably come from E is equal to P times C. photon momentum slash energy. P is equal to h over lambda. All of those Compton effect things. Delta lambda equals h over mc times 1 minus cosine theta, the scattering angle of the photon. E is equal to hf. E is equal to hc over lambda. All of those equations illustrate wave-particle duality. So whatever question you see, do it, and then figure out what you did, which principle you used to solve it. Okay, let's take a look at an example to put this into action, okay? We're going to solve the problem, and then we're going to identify which physics principles we used to solve the problem. The examples that I give you, by the way, in this handout tend to be either slightly harder than average or quite a bit harder than average. Okay, I've picked ones that I think are harder than average. The first one I would say is slightly harder than average. The other ones I would say are probably a fair bit harder than average, likely harder than what you're going to see on your exam. First one's pretty good though. A little bit harder than average, but not bad. It talks about a cyclotron. It's a particle accelerator that can be used to accelerate charged particles to very high energies. Listen, I'm just going to summarize what this says here, okay? Basically says that, look, you inject protons right here, and these protons accelerate across this d separation, and then they go in a magnetic field in a circle. And then they accelerate, and then they go in a magnetic field in a circle. And then they accelerate, and then they go in a magnetic field in a circle. And so on and so on and so on. Because they keep accelerating, the radius of the circle keeps getting bigger, and they end up spiraling outwards as opposed to going in one complete circle. Make sense? So during this d separation, we got charged particles accelerating. And in the d's themselves, we get charged particles going in circles in magnetic fields. Okay, that's the situation. You can see that we have a little bit of data given to us here right above the diagram. All right, what's the question asks us for? The radius of curvature of the path of the proton in the D immediately after it's crossed the separation. So what's the value of the radius right in here as it's going around in a circle after it's gone across the D separation? Tell me something you know about this. Tell me something that's valid that you can try for this. Yep. Okay, it's accelerating across the potential difference. What do we do when a charged particle accelerates or speeds up across the potential difference? It's like a car going down a hill, right? What do you do when a car goes down a hill? EI equals EF. That's what I'm going to do over here as well. We're going to say EI equals EF. In this case, it says it starts with a speed of 2.5 times 10 to the 6. So we're going to say EI is 1/2 mvi squared plus QV equals 1/2 mvf squared. Okay, good. That's going to get us VF. Okay, I don't know what that value is right now. Probably something times 10 to the 6 meters per second. It's going to get us VF. Now what? Hey, Logan just recognized that a charged particle speeds up across a potential difference. Good. What else do we have here? You don't necessarily have to know how you're going to use it. What else do we have here? What other situation do we have? Yeah. Good. FC equals FM. Good. Charged particle going in a circle in a magnetic field, right? You don't have to know how you're going to solve for R here yet. Okay, but you have to know that this principle applies here. So we're going to say mv squared over r equals qvb. One of the v's cancels. I'm going to solve for r here because it gives me mv over q times b. I know the mass of the proton. I know the charge of the proton. I know the magnetic field is given to me. I can solve for v over here and then sub it in right here, and I can solve for r. Got it? Good. Done. Done this question. What principal number is this over here? Look at your data sheet, right? Look at that data sheet. What principle was that? EI equals EF, yeah? It's going to be principle, no, not 4. It's going to be principle 5, conservation of energy. So let's write that in right there. That's principle 5. What's the other one? FC equals FM. Let's go back to our data sheet again. FC equals FM is which principle? Emma? 2. So it's principle 5 and principle 2. Now look closely at what the question said here. Question said, 2 physics principles used first and used second. Some of you guys are going to look at this and say, man, I used this one first and this one second. But then some of you are going to say, well, I started with this one, and then I went to this one, and then I went back to this one. So which one's first, which one's second? Here's a rule of thumb. What got me the answer? This got me the answer that I wanted, right? I was solving for R. This is the equation that got me the answer, right? So principle 2 is what I used last. Principle 5 would therefore be what I used first. Leave the last 2 boxes blank. The answer would be 5-2 here. Not 2-5, 5-2. Because it's whatever you use first, I don't really care. Look at which one you use last and write it down second. And then the other one is just going to be the one that you list first. It's a little bit of a game that we got to play, because sometimes you might have tried this one first, then went to this, and then went back to this one last. I don't care. The one you did last is the one you list second, and then the other one is the one you list first. Now, there could be another possible solution to this question. And in fact, there is, using different principles. We could have, this would not be anywhere close to the most efficient way to solve this, but we could have said E is equal to delta V over delta D to get the electric field. Then we could have said F is equal to Q times E to get the force. And then we could have said A is equal to F over M to get the acceleration. And then we could have said VF squared is equal to VI squared plus 2AD to get the final speed. And then we could have plugged that into here and gotten the exact same answer. Make sense? What would my physics principle be there? The other physics principle that we're using here in this scenario is principle number 1, accelerated motion. So we'd list our answer there as the second principle that we used, or the last principle that we used was principle 2, same as it was up here. That's a uniform circular motion. But then the first principle that we used would have been principle number 1, accelerated motion. They would accept principle 5, 2, and they would accept principle 1, 2. Either one of those would work. Every once in a while, you get a question where there's 3 principles that you've used in the same question. Pick 2 of them. You don't have to list 3. Pick 2. And just list them in the order that they were used, and you're good to go. There's often several answers that they'll accept for these numerical response questions. Okay? I promise you, any way you think of doing it, if it's legitimate, they will have thought of, and they will key it correctly. So don't worry if it's the most efficient way. Don't worry if it's the best way. If it's a correct way, it will get marked correct. We're going to take a look at one more of these examples. It's going to be scenario number 3 that's on the handout that I gave you on Google Classroom this morning. It says electrons are accelerated from rest by an electric potential difference of 300 volts. Listen, I'll tell you what, regardless of what's being asked here right now, I just noticed something. Electrons are accelerated from rest by a potential difference of 300 volts. I know right now one of the principles I'm going to use. Which one is it? When electrons are accelerated from rest, we know right away it's going to be principle number. Okay, what's it called? Yeah. So it's acceleration chamber. And what do we do in the acceleration chamber? You could do uniform acceleration. Yeah, you could. Yeah, you could. That's probably not what I would do. Nick, what would you do? Which is uniform acceleration. Yeah, that works. Okay. I'm going to probably use number 5. EI equals EF, right? EI equals EF. I'm just going to write that down right now because I thought of it. So I don't forget it later on. Now, I have no idea what I'm even being asked for, but odds are I'm going to end up doing this. The electrons enter a region that contains mutually perpendicular electric and magnetic fields. Here's the electric field strength. Here's the magnetic field strength. All right. So we've got an electric field that goes this way, and we've got our magnetic field that goes into the page you can see here. We want to find the magnitude of the acceleration experienced by the electron as it enters this section here. All right. What do you want to do first? What do you want to do first? Okay, let's do EI equals EF. In this, what's kind of color coded here. Green will say EI equals EF. And this one you could do a uniform acceleration. You could say, let's find the electric field strength. Okay, and then use F is equal to Q times E, and then use A is equal to F over M, and then use VF squared is equal to VI squared plus 2AD. But it probably stands to reason that this is going to be an easier way and a quicker way of doing it. QVI is equal to 1/2 MV squared. Let's get this value. It is an electron, 1.6 times 10 to the minus 19. The potential difference across those two plates is 300 volts times mass of an electron. Now let's solve for V here. So what do we got here? 1.6 times 10 to the minus 19 times 300 times 2, take the half over by multiplying by 2, divide by 9.11. And then let's square root that to get V. We end up getting 1.0265. Times 10 to the 7 meters per second. Good? Okay, we just got something. Yep. No, I think I did the 1/2.
You did it by multiplying.
Yeah, instead of dividing by 1/2, I ended up multiplying the left side by 2. Okay, there's my speed. Now what? Over here, this is a little bit trickier. Over here, I got two forces. And what should you do in any context when you have two forces acting? Here's my electron that's moving to the right. That electron experiences an electric force this way toward the positive plate, and it experiences a magnetic force this way. Thumb direction of the particle, fingers field, palm points downward. How do I know the magnetic force is bigger? I've drawn it bigger. How do I know that the magnetic force is bigger, Logan? Because it's following a path downwards. Right. Okay, let's say F net is equal to the sum of the forces. That's Fe plus Fm. Let's say Ma is equal to Q times E plus QVB. Q's don't cancel here because it doesn't appear in the first term. We know the mass of the electron is 9.11 times 10 to the minus 31. Solving for A, Q is 1.6 times 10 to the minus 19. We must know the electric field between those two plates. Yep, 8.5 times 10 to the 5. I didn't do that. Plus QVB. We know the speed of this. We know the speed of it because we found it, right? 1.0265 times 10 to the 7 times the magnetic field strength, which must be given to me up here somewhere. It is 0.20 Tesla. Now, you have to be careful of signs. The electric force, you can see, is upwards, so let's make that positive. The magnetic force is downwards, so let's make that negative. We can solve for A here. That's my answer. I'm done. Well, once I solve for that, let's say, let's get the magnetic force there. That's my speed times 1.6 times 10 to the minus 19 times 0.2. There's my magnetic force. Let's find my electric force now. 1.6 times 10 to the minus 19 times 8.5 times 10 to the 5. Subtract my magnetic force. Let's divide that by the mass. And we get 1.49 times 10 to the 17. So my answer here would be what? My answer here is what? A, B, C times 10 to the negative CD. Oh, that should be a positive CD, eh? That's a typo. That should be a positive CD. Should be 1517. That typo would not occur on a diploma exam. When they've put that into the booklet that I got this from, they've just typed it wrong. They've just made a mistake with that. That would not happen on a diploma exam.
What about the key answer? That's different as well.
Sorry, did the math wrong there. We do end up getting 2.11 times 10 to the 17. Which is 2117. Good? Okay, what are my physics principles? Quick. Physics principles, which one is this one? Principle 5, conservation of energy. Which one's this one? Uniform motion? Is it moving at a constant velocity? I just found the acceleration. It's not moving at a constant velocity. What principle did I use if I just found the acceleration? That's a gimme, right? If you find the value of an acceleration, then you've used acceleration. And the answer would be principle 1. So we're going to say this one is principle 5 and principle 1. Which one am I going to list first? In order, right? Used first, is it principle 5 or principle 1? Number 1 got me the answer. List that second. Number 5, I don't care what order you really did it in. Okay, if number 1 got me the answer, number 5 gets listed first. So we'd express that on our answer sheet as 5, 1, blank, blank. Got it? That's a tough question, eh? Yeah, that's a tough question. I think it's doable, but it's definitely a tough question. Okay, it's not going to be doable by everybody. It's harder than average.